Today we're going to do section 3.5. We're going to finish it up. It's going to be kind of part 2. This will wrap up what we were doing. In class today we did 3.5, then we spent the rest of the time doing 3.2 homework questions, which those will be posted in the module in a little bit. So first example we started out with was kind of a little reminder example. So we're going to say f of x equals 3x squared minus 4x plus 2. And we want to find what is f prime and f double prime. So to find f prime, we take the derivative. We're going to use the power rule. So the 2 comes down, hits the 3 that's there. That makes a 6. We get the x to the 2 minus 1 is a 1. So it's 6x to the first, but we don't write the power 1, so we're just going to leave it as 6x. Negative 4x, well, the x will drop. That'll leave us negative 4, and the derivative of the constant 2 is 0. So we get 6x minus 4 here. So now for f double prime, we take the derivative of the 6x minus 4. So 6x has derivative 6. Negative 4 has derivative 0, and this gives us our answers. So for that starting function f of x, this is f prime and f double prime. Okay, so next example comes from the textbook. We're going to do example 5. And so this says acceleration of a ball, so a of t, the acceleration of a ball, so we want to find a of t, the acceleration of a ball tossed vertically into the air with initial velocity 12 meters per second. So we want to say, how does a of t describe the change of the ball's velocity as it rises and falls? So how does a of t, we'll just say, affect the ball's velocity? Okay, so we're going to go back to solve this. We're going to go back and we're going to use a couple of the equations from section 3-4. These are those Galileo equations, which are, we have one for position, which the position equation is s of t equals s naught plus v naught t minus 1/2 gt squared. There's one for velocity. Velocity is v of t, which would be v naught minus gt. And we want to remember that velocity is equal to the derivative of the position function. So when we want to get acceleration, which is a of t, oh, we should say also the g in this, g is 9.8 meters per second squared. So a of t, if you remember that velocity is the derivative of the position function, acceleration is the derivative of the velocity function. It's also the second derivative of position. So we'll look at the velocity function and say, instead of taking the second derivative of the position, let's just look at the velocity function and take the derivative of that. V naught, that is a constant, so that's going to go to 0 when you take its derivative. Oh, and I wrote g, I wrote it accidentally as g of t. This is, I don't want to do it that way. This is just the function g multiplied, so it should be g times t. So it's like that. So derivative of v naught goes to 0. Negative gt just like that's going to be like whenever we had the derivative negative of 6x and it became 6, or you could say the derivative of negative 4x became negative 4. The derivative of negative gt is going to become negative g, which is negative 9.8 meters per second squared. So a of t is this. So it's a constant acceleration pulling down. So we'll say a of t, because we want to describe how does this affect velocity. A of t is a constant acceleration directed down. That's what this negative tells us, is that the direction is downwards. So we have a constant acceleration directed down. This slows the ball on the way up and speeds the ball up on the way down. So this is kind of describing what's going on. Since it's a constant acceleration directed down, as the ball rises, that constant acceleration pointing downwards slows the ball down until it reaches the maximum value. Then on the way, when the ball starts falling, its velocity goes negative, and then the acceleration is pulling down and the velocity is down, so then they're both pointing in the same direction, so that starts speeding the ball up. So that is basically what they wanted us to do for example 5 in the book. Example 6 in the book, we're going to do something kind of similar to it. We're not going to do the book's exact example 6, but so what we're going to do is we're going to get a graph here that's going to be f. And let's say that f of x's graph looks something like this. We want to sketch kind of a rough sketch f prime of x and f double prime of x based on the graph f of x looks like this. So what I'm going to do here is I'm going to use the slope of the tangent lines of f to generate a possible f prime graph, and then use the slope of those tangent lines of f prime to generate an f double prime graph. So our tangent lines start out as very big and positive, and they get less big and positive until they approach 0. So you have very big y values that get to smaller and smaller y values until they approach 0. So you have kind of a horizontal tangent there. Then the y values start getting bigger again. So they go from being flattened out to now the y values are getting larger and larger and larger. So larger and larger and larger positive y value, or positive slopes of tangent lines, will become larger and larger and larger positive y values. So our f prime graph would look somewhat parabolic, basically. Starting graph's kind of cubic, so this graph here will look kind of parabolic. Then if we look at the slope of the tangent lines of this graph, we get, needs a different color. We get the slopes are very big and negative, becoming less big and negative, becoming less big and negative, becoming 0. So very big and negative, less big and negative, less big and negative, 0. Then positive, then very big and positive, then really, really big and positive. So then little positive, bigger positive, really, really big. And we get something like that. Would work for our f double prime graph. So we get these two things kind of looking like that. And then the last thing we did was kind of look at we'll look at problem 39 from the homework. I'm just going to kind of draw it. And then we went on to other homework questions. So this is 39 from section 3.5, which we haven't assigned yet, and we'll get around to that in a little while. So they give us a graph A, and graph A looks like the following thing. We have kind of, let's see, 1, 2, 3. So we get kind of up here at 3, here at 2, that 1 in there. So it goes down to here, comes back up, and it turns around at 3, comes back down, sort of. Or sorry, it doesn't, yeah, it comes back down and crosses again. So graph B, we got 1, 2, 3. So graph B does, it's up here, then it goes down, it crosses over here, comes back up, and it does that sort of thing. And then graph C. So graph C goes like this. Then it comes back down a little bit beyond 2, goes down, and then it comes back up, kind of. Okay, so 1, 2, and 3. So we're supposed to find which is F prime, and F double prime. So I'm going to start looking at and kind of trying to get the pattern of the derivatives here. So we'll say, okay, A has a horizontal tangent here and a horizontal tangent here. That corresponds to a y-intercept here, or sorry, x-intercept here and an x-intercept here. A also has negative, what do you call it? Negative slopes of tangent lines here, but B is positive. So this can't, so A prime cannot be B. It's a little hard to see here, but we have kind of here at 1. So basically at this point we could say A prime does not equal B. Because even though these lined up at the correct place, this part here is negative tangent lines, and this is all positive y values. So then we say, okay, well, maybe there's a different relationship here. So let's look at kind of using different color here, and let's look at B. We could also say from this first graph, since A has horizontal tangents at 1 and 3, and C does not have horizontal tangents at 1 and 3, or sorry, C does not have y values at 1 and 3, A prime is not equal to C either. So the derivative of A is neither of these graphs. That's probably enough to say it's F double prime, but we'll kind of hold on for a second. All right, let's look at what's going on with B. So we'll use a different color. B has a horizontal tangent here, it looks at 0. Has another horizontal tangent that looks to be kind of around 2, and another horizontal tangent kind of out here beyond. So we have a 0, we have a horizontal tangent at 2, and so, sorry, horizontal tangent at 0, horizontal tangent at 2, horizontal tangent beyond 3. This corresponds to the correct x-intercepts we see here. B has negative, it's positive slopes of tangent lines here, and this is positive y values. Then a bunch of negative, so here's a bunch of negative y. So this seems okay. Let's see if B could be C. C does have the first intercept there. The second intercept on the graph here, it's pretty clear that this is at 2. And this one over here is beyond 2, so that looks like that's going to be a problem. That's a mismatch. So we can say B prime is A. B prime is not equal to C. So okay, the derivative of B is A. The derivative of B is not C. So then we're going to look at C's graph and try to decide, is C's derivative A or is C's derivative B? So C has a horizontal tangent that looks kind of like at 1 and again at 3. So C has 2 horizontal tangents that I'm seeing. They're at 1 and again at 3. If we look at 1 and 3, 1 and 3, this does not have it. So that's enough to say C prime is B, C prime is not equal to A. So what we have is B prime is A, sorry, C prime is B, then B prime is A. So we say C prime is B. So C prime is B, and then B prime is A. So this means C is F. So C is our F graph. So that when we take C prime, we get B. So that's our F prime graph. And then when we take the derivative of B, that's A. So that A is the F double prime graph. So we got basically F is C, F prime is B, F double prime is A. And that'll kind of pair up which graph is which. And that was really it from section 3.5. The rest of the class period we spent doing homework questions from section 3.2, which I'll put the solutions to those up on the classroom here in a minute.